Thank you very much, David, and thank you for the introduction and also the invitation to come and speak today. My only regret is it's not in person, so apologies for that. But as I say, thank you very much. So yes, this is one of the MinSoc lectures, slightly cheesy title for which I can only apologise. Obviously, it was going to be around platinum group elements and chalcophile elements, which is one of my sort of big areas of research, and going platinum was probably the catchiest way I could think about sort of moving up the title here. So as I say, apologies for the slightly cringe title. And this is not just, of course, sort of bits of my own work, it's bits of lots and lots of people's work in here. And there's a long list of collaborators as well, who are probably too many to mention on this slide, as well as in your own ranks, the likes of somebody like Brian O'Driscoll, amongst others as well. So I have to say a big thank you to all of those people, because ultimately this is a combination of all of that sort of thinking all together. So I wanted to talk to you today about, as I said, the platinum group elements, chalcophile elements, and particularly the sort of mechanisms of mineralisation. So there's a couple of different parts to that you can hopefully see on the slide at the moment in terms of how all deposits have formed and some of the more fundamental controls on the distribution of platinum group elements, or PGE. But I also thought it would be sensible to touch on things like the uses of platinum group elements, particularly the future uses of platinum group elements, and also the drivers in terms of some market drivers, prices, etc., etc. So hopefully this will be of interest, and I'm going to end with some sort of big questions, I think, that ultimately need to be answered for us to really move forward in terms of our understanding of how PGE and generally chalcophile elements containing deposits might form. So as David's already alluded to in terms of interests, one of my interests is critical raw materials, and I know there are lots and lots of people, including many amongst yourselves, who share that interest. And often what you find is people have that from a very specific commodity perspective. So, whether it be rare earths or something else, you might specialize in a particular commodity. And in this case, I'm going to be talking about platinum group elements, as I say. But I think this diagram is particularly useful just to think about the scale of things in terms of how much of these sorts of materials we actually produce. And you can see PGM, as they're labeled there, to stand for platinum group metals, which unfortunately is interchangeable with platinum group elements quite often. But you can see that in terms of a sense of scale for our sort of annual production in million tons, or actually on the right hand side it's more measured in 1,000 tons. So in terms of annual production for PGE, we're talking around about 400, 480, something like that, 1,000 tons per year, approximately speaking, and that's the sort of statistic that we get from something like 2017. So it's vanishingly small amounts. And critical raw materials are materials that are defined as something that has got some kind of security of supply issue, and that might be because they are controlled by one or two countries or one or two regions, because that's just where the deposits are. But that might also reflect some other factors there, whether that be sort of political unrest around sort of the mining activity itself, in terms of actually how we get this stuff out of the ground, etc. So you can see rare earth elements there as well for comparison. If we look at the table that's now on the screen, we can again make this comparison, because I think rare earths, in the sense of critical raw materials, is probably more widely spoken about. All the elements that you see listed in various shades of green there are rare earths, and as you can see, that's dominated by China. If we look at the platinum group elements, which are highlighted in this table in grey, then we see that they're mostly controlled by South Africa, or more generally, I suppose, Southern Africa, apart from palladium, which is largely dominated, the market's largely dominated by Russia. And with the exception of palladium, all of the platinum group elements, in terms of the share of production for that specific controlling country, we're talking at least 70%, if not more. And for many of these elements, like ruthenium, for example, you can see there we're talking 90+% coming from a single country. So this is a really extreme situation in terms of that security of supply that we're talking about. And arguably, in some senses, is even more extreme than some of the rare earth elements that we're looking at here as well. You're talking about very small amounts of production, but ultimately that coming from only a handful of deposits within the two main controlling countries. And besides South Africa and Russia, I should also mention platinum group elements are also produced in Zimbabwe, Canada, the US, bits in China and many other places as well, but they're much, much, much smaller levels of production. It's really South Africa and Russia that are controlling all of these things. And that has a reflection in price, because if we have some problem with production in one of these countries or in one of the deposits that controls these commodities, then we might see a shortage of supply, and so we might see a hike in the price. And this is also obviously balanced with demand as well. So the slides that you can see on the screen at the moment run from January 2000 on the left-hand side there for each plot to January of this year, 2022. And so we can compare this price to gold, and this is always in US dollars per ounce on the y-axis here. We've got the gold price through time as well. And the left-hand plot in blue, that's the line for platinum, and in red, that's the line for palladium. And typically, we tend to think about things like platinum as being the most expensive of the platinum group elements. If we think about them at all, perhaps platinum being more expensive than gold is a common idea in people's head. But actually, the price flip-flops, and certainly palladium at the moment is much more expensive than platinum. And there's only been a couple of times, historically speaking, in the prices where those two have flipped in the way that they are currently now. So that palladium is, as I say, has the higher price tag at the moment. So platinum is roughly around about $1,000 per ounce at the moment, and palladium is about twice that at just under $2,000 per ounce. But some of the other platinum group elements, and this is a group of elements that comprises 6 individual elements. So we've got osmium, iridium, ruthenium, rhodium, and then platinum and palladium, as I've already spoken about. Some of those other PGE have quite surprising price tags and uses, and it's those uses combined with a shortage of supply, even impacted by things like COVID, that have seen these sudden increases in price. So if you look at the right-hand plot, for example, the orange line is for an element, iridium. And iridium, it turns out, is widely used, or seems to be now, in the production of parts for 5G networks. So basically, in specifically the 5G network, telecommunications, manufacturing of various parts for that requires iridium in that production process. And so actually the rollout of 5G, whether we're talking within the UK or elsewhere, has driven this really enormous price spike in iridium. And that's combined with, as I say, production issues in some of the main sources, in main deposits for that particular element. And actually, as you can see there, it peaked at just over $6,000 an ounce. Iridium, I think today, is now sitting just under $4,000 an ounce, something like that. If we look at ruthenium, which is the purple line on that right-hand chart as well, then ruthenium is not quite as showy in terms of its price tag, but it's far more expensive than it used to be. So it used to be, on average, for over the last 20 or so years, sitting at around about $50 per ounce. And at the minute, it's hiked to around about $550 per ounce. And this feeds into a chip shortage, because ruthenium is used in thick film chip resistors. So this actually forms part of the issue around, again, supply issues and some sort of computing technology, etc. But all of those elements pale into insignificance in comparison to the current price of something like rhodium. So rhodium is the green line on this plot, same time period here, and we've red palladium shown again, just for a sense of scale. And rhodium, as you can see, peaked at almost $30,000 an ounce around about the middle part of last year, which is just obscene, frankly. It's a little bit bonkers. It's now currently sitting at around about $16,000 per ounce, so it's still at a really, really high price level. And rhodium is largely used at the moment in catalytic converters, and is particularly good at reducing the amount of nitrous oxide from exhaust fumes in an internal combustion engine. So that's its main use, and actually that was one of the reasons why we saw that hike in price. Various changes to legislation, including like places like in China, amongst many other places, meant that we saw this switch over to rhodium, or increasing use of rhodium, and as I say, combined with the impact of things like COVID, alongside some political unrest and various other impacts on the mining industry, particularly in South Africa, so lowering the amount of supply that we had, then we had this perfect storm for a big increase in price. So I find that quite interesting, I think, to think about the price tags associated with this. And it also shines a light on the fact that as a group of elements, platinum group elements as a whole, we're talking about 6 elements. Admittedly, I haven't shown the price of osmium there because it's traded in a slightly different way. and they tend to be co-mineralised. So they tend to occur all together at concentration. So we have to think quite a lot about the economics of what goes into processing these sorts of deposits, because, as I say, the prices of these sorts of elements are so wildly different. So I've already spoken a little bit about the current uses of PGE, but just to spend a little bit of time thinking about future uses as well, because I think this is one of the things that makes PGE in particular such an important suite of elements in terms of them as use as critical raw materials. So you may have heard, for example, that platinum is used within hydrogen fuel cells, and it's around about an ounce of platinum that's required in a hydrogen fuel cell, and that's assuming it's the sort of fuel cell system that you might have in a car or something like that. Now, arguably, the balance between EVs or electric vehicles, so battery-based transport, personal transport, versus something that's more fuel cell based is yet to be seen. And probably on a personal transport level for cars and whatnot, EVs are probably going to be the dominant form of transport. So you might say, okay, why do we care then in terms of an ounce in a fuel cell? But actually, fuel cells have lots of other uses. So, for example, if we're sticking with transport, fuel cells in particular in heavy haulage, whether that be trucks or shipping, for example, trains, etc., fuel cells are probably going to be quite important in the future. And so that catalytic property that most of the platinum group elements have, particularly platinum, palladium, and rhodium, will become particularly important as being a component of those sorts of fuel cells, or specifically, as it says there, the proton exchange membrane part of those fuel cells as well. We can also think about these things in the terms of being used in various superalloys and various other sort of photosynthesis-based systems, and also in sense of fuel cells in terms of energy storage itself, whether we look to a kind of fuel cell-based system for that storage, off-grid, for example, or large swathes of batteries. Again, that balance is yet to sort of fall out in the wash, I think, and we'll see how that progresses. But certainly there are some really important uses, and probably will have an impact on some of these prices that we see here in terms of PGE. Okay, so I've said that platinum group elements are critical raw materials, and that's largely because of their the few locations that they really occur in economic quantities in terms of, and certainly in terms of their production, the sort of number of countries that we can really seek to get these things from, they're not everywhere. And so why is that the case? And I think this is something that pretty much everybody on this call is probably considered at some point. And this inequitable distribution of deposits, as it says there, is basically an artifact of geology, right? It's a legacy, as it says, of 4 billion years of planetary evolution, driven by tectonics, by various deep mantle processes, maybe by various climatic processes as well. And all of this culminates to give us a sort of spatial pattern to where certain metals and certain materials might be found within the Earth's crust. And I just thought it might be fun to draw your attention to the article that you can see a screen grab of on the bottom left of this slide here. So in terms of amongst Cornish miners, there's a very famous phrase that people say down here, which is just ore is where it is. But actually, it was somebody like Alan Bateman, who in 1919 was, I think, the editor of Economic Geology, who wrote an editorial of why ore is where it is. And ultimately, this spatial and or temporal distribution of deposits around the Earth's crust has come from articles like Alan Bateman's there in terms of why do we see this distribution of mineral deposits. And specifically in terms of metallogenesis for platinum group elements, so the spatial and or temporal pattern of where we see PGE in the crust. If we can look to maps like this from Meyer and Groves back in 2011 to try and understand that distribution. So the yellow dots on this map are where there's a sulphide deposit that is dominantly extracted or utilised or known rather for its nickel content, but where PGE may be a co or byproduct. And the red dots on the diagram are where we know that PGE occur or are mineralised to a high enough degree to be of interest economically, even if they're not necessarily extracted at this point in time. And what we see from this map is that it's not just random distribution of where we see these sorts of sulphide deposits, specifically those containing PGE, but actually they seem to cluster with areas of ancient crust, so with cratonic lithosphere. And we also see a coincidence between where these occur and large igneous provinces. So areas where we've had extensive magmatism, we might see lots and lots of flood basalts, or we might see layered intrusions, or a combination of the two. But it's that combination of cratonic lithosphere and some kind of major melting event that means that we see these sorts of deposits occurring in that particular space. And arguably, you could make the case that that's some kind of biased preservation potential in terms of cratons are pretty stable. So if you've got some deposit within a craton, chances are it's going to stand the test of time, and we'll just find more of them because these older pieces of crust have just been knocking around for long enough to accumulate these things. But arguably, it could also be telling us about the process itself, and that's what we'll sort of carry on talking around here, I think, because it's probably telling us something about a physical or chemical interaction between the mantle plume, or this large magmatic event, and the cratons itself. So first off, how much of these elements do we actually have? And so in this table, hopefully it gives a sense of scale here. We've got everything from major element like iron, all the way down to platinum and gold. And really that line that's labeled platinum can be read as PGE as a whole suite. So that could be any of the platinum group elements that are listed there. And what we're looking at is the abundance in the mantle and the crust, just for a sense of scale. So this is kind of background, what do we have on Earth? This is what's required in a deposit. So what's the economic grade for that particular element? And therefore, what's the concentration factor that we need to go through? How much does geology have to work to go from background to some kind of economic grade? And as you can see there, for elements like iron, we're talking percentage levels that we already have on Earth into percentage levels and an economic grade in a deposit. And so we're only talking about a concentration factor of around about 5 or so. But if we compare that to something like the platinum group elements or gold, we really need to upgrade these things by 1,000-fold from the background to what we'd expect to see in an ore deposit. So geology has to work really hard to get these things to become concentrated enough that they are economic for us or feasible for us to extract in an efficient and hopefully sustainable way. So, okay, besides the background of how much we've got, we then, as I say, need geology to work quite hard for us. So we need a combination of processes and features to come together to ultimately mineralize something. And so there's lots of different names for what I suppose I'm presenting on the slide here in various different corners of the world. But to put it plainly, the recipe for mineralization probably boils down to the 4 things that you can see on the slide here. So we need a source of the element or elements, plural, that we are interested in. We need some kind of agent. So that could be a magma, it could be a hydrothermal fluid, it could be both. We need some kind of pathway, so some kind of way that we can get our agent, our magma, for example, from A to B, from the source to ultimately what ends up being our deposit. And that could be a crustal lineament, it could be something else. And then we need all of these things to combine in a level within the crust that is ultimately going to be accessible for us to find in the first place and perhaps to mine in the future. So we need some kind of deposition mechanism to happen in the right place for us and for it to be accessible. And if we put that in the context of PGE, then we can start to fill in some of these boxes more specifically. So as we've seen on the previous slide, there's slightly more PGE in the Earth's mantle than there is in the crust. We're still measuring them in parts per billion, but it's slightly more enriched in the Earth's mantle. So we probably want a mantle-derived partial melt. We need that magma to ascend from the mantle into the crust. And then we need a bunch of these mechanisms within the crust to operate: fractional crystallization, magma mixing, contamination, and perhaps some fluids and vapors to knock around the system as well. And ultimately, that should provide us with a mechanism to create a sulphide liquid to reach this point of sulphide saturation. And that's really important because platinum group elements are chalcophile, they are sulphur loving. So if we've got an immiscible sulphide liquid, sulphide separate within our silicate magma, think a kind of lava lamp scenario, then our PGE can partition into that sulphide, and we have a way of concentrating those elements further. So if we're thinking about platinum group elements, and I've already said South Africa dominates the supply, in particular, it's all coming from the Bushveld complex, basically, with a few exceptions. Most of that production is coming from the Bushveld complex. So this is a satellite image, this is a Landsat image of the Bushveld complex, and it's the areas that you can see largely in purple here. So you can see the western limb, we've got the eastern limb, we've got the first part of the northern limb up here, and there's also a southern limb as well, further south. And just for a bit of context, I mean, this is a 2 billion year old complex. This is a 2 billion year old major or large igneous province. The Bushveld complex itself is around about 4.5 times the size of Wales, because I find if you say it in square kilometres, it becomes a little bit, difficult to know exactly or relate to exactly what that figure is. But specifically the Rustenburg layered suites, the stuff that I've just pointed to in terms of basically being in purple on this image, that's over 3 times the size of Wales. And the reason that's important is because that's where our platinum group element reefs sit. They sit in a layered intrusion, layered mafic, ultramafic intrusion that's around about 9 kilometres thick, that just forms part of the Bushveld complex. It's absolutely enormous. Yet the reefs themselves may be only a metre or so in thickness. So for example, the Morensky reef, which is, there's a classic image of the Morensky reef sitting here. This is a small, tiny portion of our 9 kilometre thick layered intrusion, where ultimately the PGE has reached an economic grade. It really is like looking for a needle in a haystack. And there are other considerations that we need to have as well when we're talking about whether it be the Morensky reef and the Bushveld complex as a whole, or other PGE mineralisation. And that's where is the PGE sitting. So the PGEs, as I've already said, are chalcophile elements. So they like to sit in sulphide minerals, particularly pentlandite. And so we might be looking for some base metal sulphides in this particular deposit. Although typically the abundance of those base metal sulphides is very, very small. So there's a sulphide there, there's a sulphide liquid that was produced, but it was a very, very small volume or mass of sulphide liquid overall. They may also be sitting in discrete platinum group minerals as well, or PGM, which becomes a little bit confusing with the PGM acronym for platinum group metals. When I say PGM from now on, I mean platinum group minerals. So they may also be sitting in these platinum group minerals, and this is where we've got platinum group elements that are a stoichiometric part of that particular mineral. So rather than the PGE sitting in trace levels, maybe measured in parts per million in solid solution within a sulphide like pentlandite, here the platinum group elements may be sitting in weight percent, or rather probably tens of weight percent, and probably combined with semi-metals like arsenic or tellurium or bismuth or something like that. And so they make their own discrete platinum group minerals. And there's quite a diverse range of PGM. So we've got dozens of these things, and they're typically very small as well, whether that be around about a micron in size, as the majority probably are, even in some of these higher grade deposits, and even in the likes of Morensky reef. But then we get some bigger ones as well, maybe 10 to 50 microns, maybe even bigger in some cases. So they're small, they're diverse in terms of their chemistry. They're multi-commodity because we've got 6 platinum group elements, plus some semi-metals to worry about already, plus base metals that might be sitting in there like nickel and cobalt, and probably associated with things like chromium and copper as well. So the overall mineralogy and the overall economics of these sorts of deposits are quite complicated. And so it's not just about the grade, as it says on the slide there. We tend to think about things in terms of grams per ton for precious metals, and the tonnage itself. It's not just about those factors. If anything, for these multi-commodity ore bodies, we have to think really, really carefully about the mineralogy and the chemistry of those minerals as well. Are there penalty elements, for example, that might be sitting in that metal basket and causing us problems in terms of processing that ore? Are there other elements in there that maybe in their own right wouldn't class as a commodity that we just went out and explored for a tellurium deposit? Probably not going to happen. But if it's there in a reasonable abundance, can we use it as a byproduct whilst we're producing from these other elements from these other deposits? So in terms of crustal mechanisms now, how do we get to that stage where we create a sulphide liquid, a miscible sulphide liquid? How do we end up in the position where we get little sulphide droplets within that picture in the Morensky reef there, and maybe some platinum group minerals as well? I'm sorry, I've just seen my cat is also going to come and join the talk as well, so apologies in advance if he comes along. Should have shut the cat last night. But as you can see, there's a number of different mechanisms involved in the mineralisation. So we've got things like fractional crystallization, and that's pretty good at being able to create an immiscible sulphide liquid. But we do have to do an awful lot of fractional crystallization before we reach that point of sulphide saturation. So it's possible. We do see it, for example, in the Platinova reef in the Skagerrak complex in eastern Greenland. But perhaps it's not the most efficient mechanism. We've also got things like contamination on the right-hand side here. So if we contaminate our magma with some kind of sediment, perhaps that is sulphur-bearing, then we're going to introduce lots of sulphur into that magma, probably too much for it to dissolve and to really cope with, and so it will exsolve an immiscible sulphide liquid. So that's a really, really efficient mechanism by which to create a sulphide liquid. And we can express that according to this R factor here, which is the relative mass of silicate to sulphide liquid. And in a PGE dominated system, we need something with a high R factor. Slightly counterintuitive, I suppose, but we need something with a relatively small volume of sulphide so that we can cram as much PGE into that sulphide and therefore get the highest grade of PGE within that. But probably the most common mechanism for creating a sulphide liquid, in the sense of the most deposits that we see for PGE having undergone this, is magma mixing. And that's particularly the case in places like the Rustenburg layered suite of the Bushveld complex, amongst others. And this is where we might have a more evolved mafic magma sitting in our crustal reservoir, and we have a replenishment event with something that's a little bit more ultramafic perhaps, and the mixing of the two together pushes us into this field of sulphur oversaturation. So we create a sulphide liquid. And this graph is basically showing us the mass fraction between sulphur versus iron. So these are the classic systems by which we can create a sulphide liquid, and that's ultimately where we get the word orthomagmatic sulphides deposit, or the term orthomagmatic sulphide deposit, because there's lots of evidence to suggest that it's the magmatic stages that are of most importance in terms of forming our mineralisation. But for certain deposits like the Stillwater complex, and specifically the JM reef within that in the USA, there has been lots of evidence to suggest that it's not all about the magmatic side of the story, and that actually there's considerable hydrothermal component that is actually quite important there as well. And actually this idea is becoming more and more prevalent across more and more deposits that we look at. Most recently, I wanted to highlight the work of Katie McFall here, which is where this paper by Katie that this diagram has come from, which is on the parts of the northern limb of the Bushveld complex. And this is again finding that hydrothermal fluids probably played a really important role in, at the very least, upgrading the grade that we see in some of these deposits, particularly in areas of the northern limb of the Bushveld. But this might come at a cost. This might mean that we then considerably mess up our mineralogy in the process. We often find with these sorts of hydrothermal systems where we see PGE is that we have an even more diverse range of platinum group mineralogy. We might have smaller sulphides overall, but we're also going to find that the gangue minerals, so that the waste effectively becomes more complicated as well. So if we, for example, serpentinize large areas of our mafic and ultramafic rocks, so we convert our olivine in particular, then if you've got lots and lots of serpentine in that system, from a mineral processing perspective, that becomes really very challenging then to get a good recovery of our PGE ore. So in terms of processes, identifying whether it be something that's more magmatic based or hydrothermal, and what the effect of those two things have on the grade distribution of the mineralogy becomes quite important. And actually you can see all of these overlapping processes, I think, even just within something like the Merensky Reef in the Bushveld. And so these are sort of cartoon stratigraphy from 3 mines, pretty close together in the grand scheme of things, from the Bushveld complex, and these are all from the Merensky Reef. These are all the grade profiles of the Merensky Reef for these particular mines. So we have our stratigraphic column here, and there's the key over on the right here, and we see a similar suite of rocks and of layers, and there's certainly a pattern there that we can find. There may be some little chromatite stringers in there, sometimes more, sometimes less. But if we look at the squiggly line to the right of each of these, this is the grade profile. Okay, so this is total PGE in grams per tonne. And for reference, that little scale bar down there is 0 to 10 grams per tonne. The interesting thing, I think, is that you can see it's not the same for all of these mines. We tend to think of reefs, stratiform deposits like that in a layered intrusion to be, this wonderful layer that we can follow for tens of kilometres, and it all looks the same and it's very characteristic. And actually, it couldn't be further from the truth. We do see patterns, and we do see these things happening at a similar stratigraphic horizon or stratigraphic level. But the grade distribution might be one peak on one mine, might be 3 or 4 peaks on another mine. And that's before we even then talk about the relative distribution of things like platinum to palladium ratio or other indicators as well. So we actually look at a mineral deposit like the Bushveld, like the Morenski Reef, then we're looking at the culmination of a whole bunch of different processes, most of which are probably relatively localized. And so we're going to get a bit of a heterogeneous reef-like distribution. So it's not necessarily conducive then to us then understanding where the sort of magmas that have fed this whole system have come from and what they might have looked like in terms of their chemistry. Instead, if we want to understand parental magma, we have to reach to something else. So if we want to try and understand the regional controls, coming back to that map that I showed you earlier on from Meyer and Groves, and we need to start to look for liquid compositions. And so that might be a chilled margin or a quench, or it could just be to use the volcanic sequence that we see associated with layered intrusions, for example, or with the PGE deposit itself. So backing away from the Bushveld for a moment, we can swap to the other side of the world there in terms of looking at the North Atlantic Igneous Province. So we've got obviously a much younger igneous province that we're looking at here in comparison to the Bushveld, but nonetheless it's the one that includes the Skaergaard complex and therefore includes Platinova Reef, amongst other showings as well of PGE mineralisation. Then if we look at the lava compositions across that whole area, so the large igneous province that encompasses those layered intrusions, then we can start to map out the geochemistry of those in terms of their PGE, in terms of their precious metal content. And this is what this map aims to do. This is work from Jordan Lindsay. And so what we see is that the oldest lavas, so stuff in Western Green and Baffin Island, and sort of on our side of the Atlantic as well, this number that's written in the oval here is the platinum palladium ratio. So what this is saying is that we have twice as much platinum as we do palladium in the oldest basaltic lavas. But if we fast forward to modern day Iceland, we see that we have the flipped scenario. So we see twice as much palladium as we do platinum. And so there's a question there of, well, why does that happen? Why do we see a change in the metal basket, so the platinum palladium ratio in this case, through time and through space? What's the control within that magmatic intrusion? This is also a question of, is that real? Because it's quite easy for us to plot various things on a bivariant plot, and it's quite easy to sort of pluck some numbers out of the literature, but we do need to check that this is a real distribution that we're seeing. And so again, this is work from Jordan Lindsay, where he's tried to basically apply a kind of data science approach to all of the geochemistry that he could find for this particular area, in this case, the North Atlantic. And so without wishing to go into too much detail of this sort of data science approach, there's various different things for those of you who are into this, Disney, K-means, etc. These are basically unsupervised methods by which we can cluster data. We can end up in a situation where we basically ask the computer to plot everything versus everything else and color coordinate that in some way. And we have these two embeddings, these two axes that we can plot everything onto and color coordinate. And the sort of, in a nutshell, story of this here is the color way that you see, if it's similar between certain elements like magnesium and nickel, that means that magnesium and nickel are linked. So in terms of, we can see that they have some kind of correlation or similarity in their behavior. Every time we do this, platinum comes out as being the oddball one. Platinum never seems to behave in terms of any of the other elements that we see. All the rest of the PGE, we can see correlations with other elements, whether that be with base metals or even some major elements. Platinum never ever wants to play ball. And so really it's probably the platinum that's driving that change in platinum palladium ratio through time. And again, so we're left with this question of why. And this is where I think we need to start to look at some mantle lithology. because at the moment we're looking at liquid compositions, which is great, but that gives us a sense of homogeneity. That gives us, we can back calculate all sorts of things, but we tend to come back to a handful of compositions, and we're talking about a bulk composition ultimately. Whereas if we start to look at pieces of the mantle, whether that be in ophiolite, in the mantle xenolith, inclusions in a diamond, amongst other things, we can actually use those as pieces of a massive jigsaw puzzle to map out the distribution of PGE, whether they be in sulphides or whether they be in platinum group minerals. And so the reason this is important, this is coming all the way back now to the start of that diagram in terms of recipe for mineralisation, thinking about the source composition. And in the literature, and for a long time, in terms of economic geology, we've pretty much boiled that down for PGE mineralisation to the box model that you see along the top of the screen here. So we have a requirement in our assumptions in our model that we have a fertile mantle source. So let's say that's some kind of lertzolite. We've got lots of clinopyroxene in our peridotite. We've got some sulphides in there as well. Doesn't really matter in this case whether it's spinel or garnet bearing lertzolite, but we have something that we can melt. And we start to partially melt that. And as we do that, we're going to start to partially melt the most fusible phases, so the stuff that melts most easily. That's largely going to be clinopyroxene in this case, but it'll also include the sulphides as well. And there'll come a point where we exhaust those minerals, particularly where we exhaust those sulphides that are probably hosting our platinum group elements. And so all of these sorts of deposit models in terms of understanding of fertility require that we get to this sweet spot where we've melted just enough that we've got all the sulphide out of that mantle source, but we haven't gone too much further, because if we do, we're just going to dilute the amount of platinum group elements that we're putting into that magma. Because if they all sit in the sulphide, if you've run out of sulphide, we're not putting any more PGE into that. And the problem is, if you look at any mantle xenoliths, you don't actually see this nice one suite of sulphides, that's sitting there all interstitial to all of these other phases and therefore accessible to melting. Actually, you see there's a range of different compositions, and that may also depend on where the sulphide sits. Some of them might be interstitial, so accessible to melting, and some of them might be included within other phases, like olivine, in which case they're probably going to be locked away for a little while longer, or you really have to start melting this system quite a lot to unlock those. So this is where we can start to map out the composition of mantle sulphides in areas around the world. And so if we start with a simple system of sulphide inclusions in a diamond, and this is simple because we've only got two minerals that we need to consider here, the diamond, the host, and the sulphide. And the sulphide might have settled into or exolved into chalcophile, pentandite, and pyrrhotite, ultimately at room temperature, but probably within the mantle it's sitting at a high enough temperature and pressure that it's reasonably homogeneous. So as I say, it's a two mineral system that we're considering here. And if we map those out, what we find is that depending on the type of diamond that we're looking at, we have a different composition of sulphide associated with them, specifically a different metal budget in terms of the amount of PGE. So diamonds might be coming from a peridotite, in which case they're a P-type diamond, or they might be hosted within an eclogite, in which case they're an E-type diamond. And E-type diamonds are in blue on these diagrams, and peridotite diamonds, or diamonds derived from the peridotite, are in red in this diagram. And there's lots to take in on this slide, but the main point here is that we see that for various different elements, including the platinum group elements as a whole, there are different chemistries associated with these sulphides from various different types of diamond, and depending on the lithology that diamond has come from. If we take this a step further and start to look at mantle xenoliths themselves, so this might be, for example, a lertzolite that we see on the screen at the moment, then we're talking about an open system, lots of different grain boundaries that fluids and all sorts of melts can get along. And we're also talking about a much more complicated mineralogy now. We know we're going to have far more than just two minerals to consider here. And we can start to map out where the sulphides sit within those mantle xenoliths. So, for example, that rotating video that you see on the screen there is a micro CT scan of a little 5mm diameter plug from a mantle xenolith from the northwest of Scotland, Loch Rogue. And the white stuff you can see there is spinel, and the coloured stuff that pops up in just a second is a whole bunch of interconnected feldspars. And it doesn't matter what the colour is. If it's one colour, that means it's all interconnected. And what we find is that the sulphide minerals, there's two groups of sulphide minerals that we can identify in these sorts of xenoliths, but one in particular, which occurs as rounded droplets, sits in their quite colourful melt channels within these xenoliths. And they also seem to be associated with apatite, like we see on the lower left image here, and carbonate in a sort of almost three-way immiscibility scenario of things. And this is quite peculiar, because if we then map out the composition in terms of trace elements, platinum group elements for those sulphides, what we find is that the sulphides that are sitting in those little melt conduits and the colourful stuff on that CT scan and associated with carbonate and phosphate, they have much PGE than any of the other sulphides that we see sitting in any of those xenoliths elsewhere. So the sort of big interstitial sulphides don't have much PGE in, but the stuff that's sitting in those little melt conduits has lots and lots of PGE in, and it even has discrete platinum group minerals as well here in terms of cooperite. So we're starting to see then that there are different groups or populations of sulphide, and that they're not all the same chemistry, and they're not all the same textural environments in terms of where they're sitting within things. And that association with phosphate and carbonate has ultimately opened up some really quite curious doors in terms of the sorts of rocks we might now consider to run platinum group element geochemistry, including to understand how they might become mineralised. And so the work on the screen at the moment is by Unju Choi, who has recently completed a PhD in Western Australia. And Unju was really interested in understanding the bulk PGE geochemistry of the more exotic compositions like kimberlites, like lamprophyres and carbonatites. So the sorts of things that we think of in terms of very, very small degree partial melts, or perhaps they don't even exist as melts. It's a little bit controversial in terms of kimberlites, perhaps, but perhaps we're thinking about things that have more kind of a physical entrainment and fluxing scenario going on than traditional partial melting model that I've just outlined. And the take home from all of these plots here is that, for one, for most of these rocks, there are more PGE in them, in the bulk geochemistry, than we might expect, given that classic box model melting scenario that I outlined a few slides ago. And so it's a little bit strange then, why do we have so much PGE? And one thing that we can potentially see from mantle xenoliths is, well, maybe the partial melting tech model is not actually strictly required. Maybe there's a way we can mobilise platinum group elements some other way, whether that be in a metasomatic environment, maybe it's fluxed, maybe it's physical entrainment or something else, but it's not just this sort of simple box model of partial melting. So moving on then, if we think about sort of less traditional sources, then shall we say, of platinum group elements, moving away from that fertile lertsolite peridotite box model that so many of these sort of ore deposit models rely on, we start to look at other mantle lithologies. We've already seen mantle derived lithologies like carbonatites, etc. What about eclogites is another one. Go and have a look at the composition of sulphides within eclogites. We might expect them to not have very much PGE in, based on the fact that for those E-type diamonds, we didn't really see sulphides that were particularly enriched. So this is a false colour map from the QEM scan of an eclogite xenolith. There's a bunch of these from Roberts Victor, which is a kimberlite within South Africa, which is particularly abundant eclogite xenoliths within it. And again, we can zap loads and loads of sulphides, and we can build up the PGE geochemistry across all of those. And there's a lot on this slide, but the take-home message is each one of these boxes is a discrete xenolith, and most of them have very small abundances of PGE, except for one or two samples that have noticeably enriched PGE concentrations, whether we're looking at them on a multi-element diagram here or whether we're looking at them on a sort of bivariant plot on here. And all it takes is one or two to demonstrate that actually sometimes these more unusual lithologies can have an appreciable amount of PGE. And one of the reasons this is particularly interesting is because a few years ago, based on isotopic evidence, specifically rhenium, osmium, radiogenic isotopes, and also other radiogenic isotope signatures as well, and based on inclusions from diamonds from the vicinity of the Bushveld complex, various authors, but particularly Richardson and Shirey here, suggested that the eclogites might be a significant source of magma for the Bushveld complex. And of course, that means then quite a lot of lithospheric mantle melting. In fact, they actually started to model it, and they started to calculate how much we might need, according to where you are in the Bushveld or Rustenburg layered suite, how much of the lithospheric mantle melt component was involved and what proportion of that was coming from something that was eclogitic. And there's two camps here of people who read these papers, and some say, oh, lithospheric mantle melting, never going to happen. If it does, it would actually wipe out all of the diamond cargo that we see within the lithospheric mantle within the SCLM anyway. It can't have happened. And there's other people that are sort of vehemently for lithospheric mantle melting. I suppose I sit somewhere in the middle. But ultimately, this is all done based on isotopes, on isotopic ratios. So if we start to plug in some of the PGE compositions that we've measured from an eclogite xenolith in terms of their sulphide compositions, just to see whether that works from a mass balance perspective, what we find is that it can work. And so that's quite interesting. All of a sudden, we're not just talking about the rough mass balance based on some isotopes here. We're seeing reasonable evidence that in terms of the metal budget of the lithospheric mantle beneath the chalcophile craton in this instance, beneath portions of the Bushveld complex, it does work. There is enough PGE down there that if we were to melt that out, just mobilise those sulphides, we can accommodate and account for the PGE geochemistry that we see in the Rustenburg layered suite as a whole, and that we suggest as being a parental magma through the Bushveld. So I'm almost there. The last thing I just wanted to flag up is I've talked a lot about sulphides, particularly in the context of the mantle source region. And so we're talking about PGE, probably in parts per million, solid solution in something like pentlandite, pyrrhotite, or chalcopyrite, probably mostly in pentlandite. But ultimately in a sulphide liquid, or something that's almost homogeneous as a sulphide liquid at the elevated pressures and temperatures that we might expect to see them at within the mantle. That's all very well and good, but it might actually only be half the story. And I've already said that platinum group minerals are quite a complicated bunch of things to consider in a mineral deposit, where we might see them as larger suite of minerals. We know they exist in the mantle. We see them, whether that be in mantle xenoliths or elsewhere, and sometimes they're associated with sulphides in terms of spatially within those xenoliths, and sometimes they're nowhere near a sulphide. They're just sitting there as some strange alloy associated with an olivine crystal or something like that. So we know PGM are there, platinum group minerals are there, and they're mostly tiny when we're talking about being in the mantle, at least 1 micron, probably less than 1 micron. Mostly of these could be classed as nanoparticles. So we've got really complicated minerals, quite a diverse bunch of minerals, and they're tiny. How can we possibly quantify those in terms of how much of the metal budget are they holding? And I think that's one of the big questions that we need to address here, because we might only be considering, as I say, half the story in terms of the amount of PGE that are available to mobilise out of the mantle. And of course, that might also have implications for how we mobilise them, whether that be partial melting, or whether it be fluxing, or whether it actually be something like a physical entrainment. So I'll finish off then with probably far too much text on this slide, but for those people who are interested, and certainly for the sense of this recording, you can always pause it and have a read through. But as I've basically said, there's quite a lot to consider here in terms of the economics, the mineralogy of these sorts of multi-commodity ore bodies like platinum group elements, because we've got a suite of 6 elements plus some other stuff that might be sitting in there. And so we need to consider quite a lot, both on a practical sense, but also in our understanding how these sorts of deposits form, either from a fertility perspective, all the way through to very specific localized mineralization mechanisms. And added, PGE ores tend not to be able to see them in the field. You don't see a big fat juicy sulphide and go, aha, this is where the PGE is. There's not very much we can do, for example, using geophysical techniques to locate ore horizons directly as the ore itself. We have to use a really good understanding of mineralogy, of igneous processes, of geochemistry ultimately, to actually be able to measure these elements and identify whether they're there or not. Because we have so much reliance on sort of box models and various other things in terms of where these sorts of elements might be mobilized from, we might be blinkering ourselves in terms of the sorts of rocks that we ultimately will run through assay and identify that there's appreciable amounts of PGE there. And so aside from the sort of classic mafic, ultramafic systems, coming back to that carbonatite and lamprophyre situation and those sort of more exotic lithologies, there may be some notable exceptions that we've basically walked right over. We know, for example, Palabora, which is a carbonatite complex, which is the same age as the Bushveld, it's part of the Bushveld Large Igneous Province, that has platinum group minerals in it, that has a reasonable grade of PGE within it. And there's also the wonderfully named Mordor complex in Australia, which is effectively a lamprophyric composition, and again has things that we can measure in grams per tonne, so reasonable economic grades for PGE. So I'm going to finish off there, and I'm going to leave some of the big questions that I think I already alluded to on screen for those people that are interested. Thank you again for the invitation to talk. Cheers.